Hello, everyone. Welcome to our Deep Dive podcast, where today we'll be reviewing the paper Robust Speech Recognition via Large-Scale Weak Supervision by Alec Radford and colleagues from OpenAI.
Are you ready to explore the world of robust speech recognition zero? Absolutely. This paper is quite a milestone in the field of automatic speech recognition, or ASR. To start, can you give us a high-level overview of what the authors set out to achieve?
Of course, the main goal of the paper is to develop a speech recognition system that is robust and generalizes well across different datasets and environments, without the need for dataset-specific fine-tuning. They do this by training models on a massive, weakly supervised dataset, 680,000 hours of audio, paired with transcripts from the internet.
That's a huge amount of data, and I noticed they call their approach Whisper. What's the significance of using weak supervision at such a scale?
Great question. Weak supervision means that the data isn't always perfectly labeled. Some transcripts might be noisy or machine-generated. But by using such a large and diverse dataset, the model learns to handle a wide variety of audio conditions, accents, and languages, making it more robust in real-world scenarios.
That makes sense. The paper mentions that previous state-of-the-art models, like Wave 2 VEC 2.0, relied heavily on unsupervised pre-training. How does Whisper differ from those approaches?
Whisper takes a different route. Instead of focusing on unsupervised pre-training, it leverages large-scale supervised pre-training, albeit with weak supervision. The key difference is that Whisper is trained end-to-end to predict transcripts directly from audio, using an encoder-decoder transformer architecture.
Interesting. So they're using a sequence-to-sequence model, similar to what's been successful in machine translation and other NLP tasks. Can you walk us through the data processing pipeline they used?
Sure. The authors collected audio transcript pairs from the internet, resulting in a highly diverse dataset. They applied several automated filtering methods to improve transcript quality, such as removing machine-generated transcripts and ensuring the spoken language matches the transcript language. They also broke audio files into 30-second segments and included segments with no speech for training voice activity detection.
That's quite comprehensive. I'm curious about the model architecture. You mentioned it's an encoder-decoder transformer. What are some of the specifics?
The model processes audio by converting it into an 80-channel log-magnitude MEL spectrogram, sampled at 16,000 Hz. The encoder consists of two convolutional layers, followed by transformer blocks, and the decoder is also a transformer. They use byte-level BPE tokenization for text, which allows the model to handle multiple languages efficiently.
And they trained models of various sizes, right? From tiny to large, with up to 1.5 billion parameters?
Exactly. This allowed them to study how model size affects performance and robustness. They found that larger models generally perform better, especially on multilingual and multitask benchmarks.
Speaking of multitask, the paper emphasizes that Whisper isn't just for transcription. What other tasks can it handle?
Whisper is trained in a multitask format. It can perform speech transcription, speech translation, from any language to English, voice activity detection, and language identification. All these tasks are specified using special tokens in the decoder's input sequence.
That's impressive. How do they evaluate the model's performance, especially in terms of robustness?
They use the word error rate, or WER, as the primary metric, but they also apply extensive text normalization to minimize penalization for non-semantic differences. Importantly, they evaluate Whisper in a zero-shot setting, meaning the model is tested on datasets it hasn't seen during training, without any fine-tuning.
That's a tough test. How does Whisper perform compared to previous models and even humans?
The results are striking. While Whisper's WER on in-distribution datasets like LibreSpeech is similar to previous models, it significantly outperforms them on out-of-distribution datasets. In fact, the best zero-shot Whisper models approach human-level accuracy and robustness across a wide range of benchmarks.
That's a huge leap forward. The paper also discusses effective robustness. Can you explain what that means?
Effective robustness measures how well a model's performance on out-of-distribution datasets compares to its performance on a reference dataset, like LibreSpeech. Ideally, a robust model should perform equally well across all datasets. Whisper models show much higher effective robustness than previous supervised models.
That's a key point. What about multilingual performance? How does Whisper handle languages other than English?
Whisper is trained on 117,000 hours of non-English audio, covering 96 languages. On benchmarks like multilingual LibreSpeech and Vox Populi, Whisper performs well, especially in a zero-shot setting. However, its performance is closely tied to the amount of training data available for each language.
So, more data equals better performance, especially for low-resource languages.
Exactly. The paper shows a strong correlation between the amount of training data per language and the model's WER. For every 16-fold increase in data, WER roughly halves.
That's a powerful scaling law. How does Whisper perform on speech translation tasks?
On the CoVIO-ST2 benchmark, Whisper achieves state-of-the-art results in zero-shot speech translation, especially for low-resource languages. This is attributed to the large amount of translation data in the pre-training set.
And what about language identification and robustness to noise?
Whisper's language identification accuracy is not as high as some supervised models, partly because it lacks training data for some languages in the evaluation set. However, it's much more robust to additive noise than models trained only on clean datasets like LibreSpeech.
That's crucial for real-world applications. The paper also discusses long-form transcription. How does Whisper handle audio longer than 30 seconds?
They developed a buffered transcription strategy, where the model transcribes consecutive 30-second segments and shifts the window based on predicted timestamps. They also use beam search and temperature scheduling to avoid issues like repetition and hallucination.
That sounds effective. How does Whisper compare to commercial ASR systems in long-form transcription?
Whisper outperforms the best open-source models and is competitive with, or better than, commercial ASR systems on a variety of long-form datasets, including TED Talks, podcasts, and interviews.
That's impressive. The paper also compares Whisper's performance to professional human transcribers. How close does it get?
On a subset of the Kincaid 46 dataset, Whisper's WER is only slightly higher than that of professional human transcribers and even beats some computer-assisted transcription services.
That's remarkable. Let's talk about scaling. How does increasing model size and dataset size affect performance?
Both model size and dataset size lead to improved performance, but with diminishing returns as you approach human-level accuracy, especially for English speech recognition. For multilingual and translation tasks, scaling continues to yield significant gains.
Are there any downsides to multitask and multilingual training?
For small models, there can be negative transfer. Joint models may underperform compared to single-task models. However, as model size increases, multitask and multilingual models start to outperform their single-task counterparts, showing positive transfer.
That's good to know. The paper also discusses text normalization. Why is this important?
Text normalization ensures that WER reflects genuine transcription errors, not just formatting or punctuation differences. The authors developed a custom normalizer to better align model outputs with human judgment.
What about decoding strategies for long-form transcription? Any tips from the paper?
Yes, they recommend using beam search, temperature fallback, voice activity detection, previous text conditioning, and initial timestamp constraints to improve reliability and reduce errors in long-form transcription.
That's a lot of engineering. The paper also reviews related work. How does Whisper fit into the broader landscape of speech recognition research?
Whisper builds on decades of progress in scaling models and datasets, multitask learning, and robustness research. Its main contribution is demonstrating that large-scale, weakly supervised pre-training can yield robust, generalizable speech recognition systems.
Are there any limitations or areas for future work mentioned in the paper?
Yes, the authors note that Whisper's performance on low-resource languages is still limited by data availability. They also suggest that improved decoding strategies, fine-tuning, and incorporating unsupervised objectives could further enhance performance.
That's exciting. Before we wrap up, can you summarize the key takeaways from this paper?
Absolutely. Whisper demonstrates that scaling up weekly supervised pre-training can produce speech recognition models that are robust, generalize well across tasks and languages, and approach human-level accuracy without the need for dataset-specific fine-tuning.
That's a game changer for the field. Thanks for walking us through this paper. Any final thoughts?
Just that Whisper sets a new standard for robust, general-purpose speech recognition. It's an exciting time for ASR research, and I'm looking forward to seeing how the community builds on this work.
Me too. Thanks to all our listeners for joining us on this deep dive. We hope you enjoyed our review of robust speech recognition via large-scale weak supervision. Until next time, stay curious.
To summarize, this paper shows that large-scale weekly supervised pre-training enables robust, generalizable, and near-human-level speech recognition across languages and tasks, setting a new benchmark for the field.